Hi, everyone. Welcome. Our next speaker will be Manojit Nandi, talking to us about measures and mismeasures of algorithmic fairness.
How do I do things? There we go. That's how things happen. Okay. Sorry for the bit delay. Hello, everyone. Thank you all for coming to my talk this afternoon on measures and mismeasures of algorithmic fairness. I'm Manojit Nandi, and I'm a data scientist. So, a quick about me. According to the Google Cloud Computer Vision API. So, I ran a photo of myself through the Google Vision API, and it produced some labels for me. So let's go through some of them and see how right they are. Am I a dancer? Yes, I'm an aerial dancer and a circus acrobat. I just work as a data scientist for 40 hours a week because I gotta pay rent somehow. Am I entertaining? I hope so. You're stuck with me for the next 40 minutes. Am I fun? Most of the time. And lastly, am I a girl? So that one is not true. I am a male presenting cis man. So why did Google Vision think I am a girl? And the thing is, it's not just Google Vision. If I were to run this through Microsoft's Vision API, it produces similar results. It says, oh, this is a picture of a lady. And so the thing is, like, what are these really looking for when they say this is a girl? Are they saying, how similar am I to what they've understood to be a girl? Is it because of, oh, this is a dancer, and all the dancers in my training set were girls, so therefore this is a girl as well? Or is it some physical feature about me that makes it think that, oh, this is probably a girl? And this seems like a fun, innocuous example, but these types of systems of automatic gender recognition are used everywhere. For example, to basically show you better ads when you're in a taxi cab for some reason. Because after all, is not the true purpose of data science to show you better ads? And the thing about this is, it sounds really dumb, but it's actually quite dangerous. Because if you basically have some prototypical understanding of like this is what a man looks like, or this is what a woman should look like, you can actually misgender people whom that is actually a huge issue to. And so there's a researcher at University of Washington, Os Keys, and who's done a survey of how queerness and gender are thought about in human-computer systems. And their overall findings is that the way we think about gender in human-computer systems is inherently trans-exclusionary. So now as we try to be like data-driven leaders and we use these types of systems, we are sort of using systems that are inherently trans-exclusionary. We inherently make decisions that ignore the existence and lived experience of the trans community. And I hope this example sort of motivates why we should care about fairness and ethics when we do data science and machine learning. So what is algorithmic fairness? So algorithmic fairness is a field of research that's aimed at trying to mitigate the effects of unwarranted bias on or discrimination on people in machine learning. And so this is a kind of weird thing, because like bias is a very overloaded term in data science and machine learning. It's probably the second most overloaded term after kernel, which has a bunch of different definitions in machine learning. And right now, sort of like the focus on this type of research has been in like coming up with mathematical definitions of fairness. We have this mathematical definition of fairness, we're going to find some solution to it, and hope that maps back well to the original problem. But over the last year or so, we've seen some pushback against this. We've seen that, okay, in this paper, for example, called Fairness Abstraction in Socio-Technical Systems, that there's sort of a formalism trap, that we care too much about mathematical formalisms, that even if you solve the mathematical formalism, it doesn't really translate well to a real-world solution. And the key thing to keep about this is that fairness is inherently a social and ethical concept. It cannot be perfectly captured or represented through mathematical definitions or statistical metrics. And we'll talk about the research, and I guess I want to take a slight, aside about like this idea of like, okay, well, we're using algorithms and math can't be racist. That's silly. And this actually came up in January when this like alt-right journalist basically criticized the New York Congresswoman Alex Ocasio-Cortez when she said that, okay, algorithms have been shown to discriminate against blacks and Hispanics in different cases. And so the thing is that, like, when we say that an algorithm is racist or sexist, we're not saying that like math is inherently racist or sexist. We're not saying that like the prime numbers are inherently racist or logistic regression is like inherently sexist. We're talking about the ways we use math, the ways we use algorithms can reinforce societal inequalities. You know, prime numbers are not racist, but the way we can use prime numbers to break cryptographic systems has real-world implications. The way we use logistic regression to decide who gets a credit loan or a bank loan or not has real-world implications. And that's what we need to think about when we design these algorithms. They're not sort of just existing in the void by themselves. They're embedded in human systems. And on the research side of this algorithmic fairness, so now there's a field called Fairness, Accountability, Transparency, FATSTAR ML. And this is like this interdisciplinary research area about how can we get machine learning and technical systems to care about ideas like fairness and justice and equality. And it's really exploded over the last few years. You're seeing a dedicated conference to it, ACM FATSTAR, which was held in Atlanta. We have seen lots of open source libraries about this. And even at this conference, we actually have another talk about model fairness later today. And I do, for anyone who's also interested in attending that, I have looked at that other talk. I do believe there's enough differentiation between our two talks that you would get something about worthwhile by attending both talks, for anyone who has a slight concern. And it's not just researchers who are talking about this. We talk about this in popular media, too. So Weapons of Math Destruction by Kathy O'Neill, Automating Equality by Virginia Eubanks, and Algorithms of Repression by Safia Noble. And so, you know, the big three. And I think they take this interesting approach of like, okay, here's how the algorithms work on the people. Like, we as a data scientist, we as the machine learning researchers are sort of separated from the downstream effects of how our work impacts the general humanity and general society. And the thing is, like, as data scientists and like computer science, we're sort of trained in like math and statistics. We're not trained to think about ethics. We're not trained to think about public policy. But we do need to understand that like our work has downstream implications. I think deep down, like we may not be comfortable like taking the role of an ethicist or taking the role of a public policy, but I think deep down none of us want to cause the apocalypse. None of us want to do harm to others. Like no one wants to be the people written about in these books. And I think the way that they attack this problem of like talking about the dangers of these algorithms and like how these hurt people is an interesting perspective from just research, which is just like, okay, here's the cool things we could do, whereas these popular media talk about like how could this hurt people? And talking about how could this hurt people, well, you have to think about like, okay, maybe you don't really care about the moral side of like I don't want to hurt people, but I can maybe encourage you to think about these types of problems by legal regulations of you maybe don't care about hurting people, but you do care about keeping your job, because if you break some of these things, well, you're violating legal laws, and then you can lose your job because your company will be fined millions of dollars. And so in the US, for example, we have disparate impact laws which which basically regulate how you can give out loans, how you can hire for people, such that you don't harm them. And also in the EU, we now have GDPR, which is an overarching holistic set of laws and rules of like how we should think about the way we use algorithms to process people's data. And we have to think about, okay, can you explain why your algorithm made a decision? Can you explain why your neural network didn't give someone a loan? And can they opt out of that as well? And so let's talk about the different types of algorithmic biases. And so this is based off some work by researchers at Microsoft and Research and Cornell. And this was presented at the conference that is now NEURIPS, NEURIPS. Someone told me it's pronounced like Europe, and I'm not actually sure if that was a joke or not. But really, these researchers sort of identified three big categories of way we think about like algorithmic biases of like where we are now, where we're heading, and where we need to be. So first, let's talk about where we are now. So a lot of problems in algorithmic biases focus on this problem of allocation. Who gets a loan or not? Who gets a job? And these are really just like binary classification problems of like, do men get software engineering jobs more than women? Do whites get credit loans more than non-whites kind of thing? This is a binary yes or no. And this is really what most of the research has been on now, because it's sort of easy to formalize as a mathematics problem and easy to solve. And so this was in the news, big story last year, was that Amazon had to scrape their AI recruiting tool because they found out that it was discriminating against women. It was basically looking at things of like, oh, hey, if you have a name like Jared, or you were on the lacrosse team back in college, you're probably more likely to be hired as a software engineer, which really makes no sense. And so they had to scrape this because they realized, oh, hey, we were harming or choosing our model was selecting against women, but if we use this. Next, let's talk about where we're sort of heading. And so next is this idea of bias representation. And so this is focused on looking at like how harmful stereotypes or harmful labels are propagated through machine learning systems. And these are often related to like language problems or computer vision problems, which are like the neural network problems of it just picks out a solution and does some black box neural network magic, but we don't really care about why the inner mechanics of what it's doing. And these are sort of harder to quantify the errors compared to those previous bias and allocation problem, which is why there's less research on this now, but like we're starting to think about it more. And so there's this famous example that when Google Photos was deployed like 2015, that it accidentally labeled a group of black kids at a graduation party as gorillas. And so for those of you who are not familiar with like history of US, I don't know if it also applies to other Western countries, but gorillas or apes has been historically used as a derogatory slur against African Americans in this nation. So this label, like, one, is wrong, but two, it also invokes harmful stereotypes against African Americans. And the thing is like, it's harder to quantify as an error, because yeah, this is a wrong label, but at the same time, Google Photos is never going to label a group of white kids as gorillas. This is specifically a label it gives to these kids here, and it promotes this harmful stereotype. And other examples that are sort of hard to quantify are Snapchat filters, for example. So when you apply a Snapchat filter, flower crowns, it sort of brightens the skin of the individual. Why? Because Snapchat filters have sort of learned, okay, brighter skin is associated with prettiness. Therefore, when I apply the filter, brighten their skin. And so if you think about that, it's like really hard to quantify what's wrong. It's doing the optimization process it's supposed to do, but there's just something about that solution that just sits uneasy with you. And another example is Google Translate. So when you translate sentences from like Malay, which is a language that doesn't have gendered pronouns, so you can have like, they are a doctor, they are a soldier, they are a professor, they are a prostitute, they are a nurse. But when you translate to English, it sort of automatically genders them. He is a doctor, he's a soldier, he's a professor, she is a prostitute, she is a maid, she's a nurse. And at the same time, like, Google Translate is doing this mathematical optimization. It's like hard to say why this is wrong. This is a valid translation of those sentences, but there's just something about it that just sits uneasy with you. And to give credit to where it's due, Google has actually made a sort of hot fix where when you translate from a non-gendered language to a gendered language, it will actually show both gendered ways. So translating from they are a doctor, it translates to she is a doctor, he is a doctor now. So this is like a quick fix for this. It's still not available on the like iOS and Android version of Google Translate. And you still see like some of these biases when you do Google autocomplete. So if you type in a search of he is a blah, you'll probably get doctor or soldier more than if you do she is a blah in Google autocomplete. Finally, where do we need to be? And so this last version is called the weaponization of machine learning. And so the key idea of this is that, like, as data scientists, we're taught to train models, we produce some metrics, but we don't really think about how our work can harm people or how it could be misused. And so there's this big story back in 2017. A group of Stanford researchers tried to create a classification algorithm that tries to predict people's sexuality or sexual preferences based on images of their faces. And so they effectively said they created a gaydar of trying to predict if someone is heterosexual or homosexual. And the thing about this is, there are countries in this world where homosexuality is criminalized by the state. If you are out as a homosexual, you will be executed by the state. And there are plenty more where it's like, it's not criminalized, but it's really dangerous to be out as a homosexual. So if someone takes this model, they could use it as a weapon against homosexuals in those countries. And the thing about this is, there's no mathematical measure, no unit test you can write that can tell you, this is a bad idea, you shouldn't do this. This is really going to require you to have cultural anthropologists and historians in the room to tell you, like, hey, this can harm people. And that's why I'm really glad that there is sort of this starting discussion of like having data scientists and machine learning technologists really think about ethics training. Like when you do degree programs at like UC Berkeley or Carnegie Mellon, they're starting to include an ethics component. Well, I don't think that will really fully solve this. I do think it's the start of developing a different tech culture that really cares about the downstream effects of our work on people who are not like us. So let's talk about the different types of fairness measures. So these are like the mathematical definitions, and I will really talk about like what they are and some of their big weaknesses of them. And so this is based off of work by two Stanford researchers, Sam Corbett-Davies and Sherrod Goel. And they're based on this paper, Measures and Mismeasures of Fairness, which this talk is the title of this talk is based on. And so let's talk about different definitions of algorithmic fairness. So there was a talk a year ago by this Princeton professor, Arvind Narayan, where he really showed that, okay, there were 21 definitions of algorithmic fairness at the time of when he gave that talk. Now there's more than 30 definitions of like algorithmic fairness now. And think about this, like, as computer scientists and like statisticians, we think, okay, there's 30 definitions. There's got to be like some that are better than others. There's got to be like this one true definition of fairness we can use. And that's not really true. Why? Because fairness is a social and cultural concept. Like what was considered fair 50 years ago is not going to be considered what we consider fair now, and what we consider fair 50 years from now is different from what we consider fair today. But these 30 so definitions of algorithmic fairness can be broken down to 3 big groups: anti-classification, classification parity, and finally calibration. And I'll just give a quick warning. This is where the talk gets a bit more technical and mathematical. So first up, there's these anti-classification measures. And so what these are is that, okay, you have these protected features, such as like race, gender, religion, place of origin, and you have unprotected features for your model. And the way that these anti-classification metrics work ideally is that, okay, when you make an algorithmic decision, it should effectively ignore those demographic features. It should ignore race, it should ignore gender, it should ignore religion when it makes this decision, or behave in a way it does so. It's sort of this idea of individual fairness. You judge a person by the content of their character rather than the color of skin, kind of thing. That 2 people should be treated equally if they have the same unprotected features. But the thing about this is that like you can't just like throw out race and gender from your model or from your data set and say, okay, I'm done. Because we're now starting to realize that there are proxy features that we have to worry about. Like features that are not directly encode race or gender, but are highly correlated with them. And so, for example, there's this story back in like 2012 when the office supply company Staples, they did a promotion that if you live within 20 miles of a competing store, we will give you a special coupon discount so that you'll come to our store instead. And the thing is, the people who live in those like neighborhoods at 20 miles from the competitors, those are sort of like wealthier suburban neighborhoods. And the people who live in wealthy suburban neighborhoods have certain racial demographics, for example. So when your model discriminates or makes a decision based on location, it's inadvertently acting as if it was making decisions based on race. And so Staples was hit a huge fine with that for disparate impact. And as a result, these types of features are very useful for designing fairness-aware models. So what is a fairness-aware model? So it's sort of like a traditional machine learning supervised model, except now we have this added component. We need to think about those protected features. So when you have to do standard machine learning, you have your features X and your labels Y. And you basically want to map the features X to the labels Y. Well, now with fairness-aware algorithms, you have X, you have Y, and you have your protected attributes. So race, gender, religion, place of origin, as a protected class Z. And what you want to do is like you want to like learn features that learn your label. So you want to learn who to give a loan to, but you don't want to accidentally learn race or gender. And so one really cool algorithm that does this is fairness-aware GANs. So I think this is a really clever idea. So how this works with GANs is that you sort of have like these 2 sub-models. One is sort of like your standard machine learning classifier. It's trying to like take the features and learn the labels. The other one is trying to take the labels and learn a protected class. And so the way you can think about it is it's sort of like this duel. Like I'm trying to learn a good classifier. You're trying to break me by saying, oh, that classifier accidentally learns race or gender. And so this is how that really works. It's like you have to look at this loss function. So like the one in the red box is sort of saying, am I a good classifier or not? Am I learning features that predict who gets a loan or not? The one in the blue box is saying, okay, you learn who to give a credit loan to. Are you accidentally learning race or gender? Is your basically who gets a loan or not basically just figuring out, is this person white or non-white? And sort of this trade-off, if you really squint your eyes at this, if you studied machine learning and regularization, so like ridge regression or lasso regression, if you squint your eyes at this and stare at it deeply, it kind of looks like a regularization of, I want to be a good classifier, but I don't want to be overly complex. In this case, complex is sort of like, I don't want to accidentally be discriminatory. And this is sometimes referred to as this accuracy-fairness trade-off. And I'll be really honest, I don't like that this is referred to as a trade-off. Because if you really think about it, like, why are we doing all this stuff in the first place? Because our training set is biased, because our testing set is biased, and that means our testing labels are biased. Like, our answer key is wrong. We don't want models that perfectly learn the testing set labels, because then it's also learning those biases as well. So we expect the accuracy to go down, and I also really don't like calling this a trade-off, because it sort of ties into this like very harmful idea that somehow promoting diversity requires you to partake in suboptimality. And so you see this in like tech hiring, where okay, if a software company says like, oh hey, we have our 50% of our software engineers are women, that's a good thing. But then there's always like some loser on Twitter is like, hey, I got a brilliant idea. Instead of hiring people based on their gender, what if we hire the most talented person for their job? And this is sort of like ties into the harmful idea. Like, in order to get diversity, you have to pick less optimal candidates or less skilled candidates. And that's not true at all. Like, diversity is very good for tech. Having people with different lived experiences and different ways of thinking in the room is important because they can call you out when you're being stupid. And that's very important in data science. And so what are the dangers of using these anti-classification measures? Like, okay, this sounds like a good idea. Like, we should judge people based on their important characteristics and not accidentally learn those protected features. Well, by removing those protected features, we're sort of ignoring the underlying process that acts on different demographic groups. Like, these metrics sort of look on making the outcome equal. But really, fairness is making the process equal. And so one way this is a danger is sort of prison recidivism. So who gets, when you're a prisoner and you're defending, like, do you get released on bail or not? And so how prison recidivism works is like there's this algorithm, COMPAS. It gives you a score between 1 and 10, which is sort of like how risky is it to let you out? Like, what's the likelihood you will commit a crime if we release you? And the thing is that male defendants are more likely, for the same score, male defendants are more likely to reoffend than female defendants. So if you ignore gender in this case and sort of average the two lines, you sort of get that average line that's higher than the female defendant rate. And so if you cut your threshold off like a little below 60%, whereas if you just looked at gender exclusively, you would say, okay, we don't release female defendants when they have a score of 8 or above. Whereas if you take the average and you now have that threshold, we don't release anyone if it's like 7 or above. And thus, you're now detaining more women than you originally done if you had looked at gender separately as a feature in this. So next is classification parity. So classification parity is sort of an extension of like traditional machine learning. With machine learning, you evaluate your model according to some metric like accuracy or precision or recall or AUC. Whereas now, you take those metrics and sort of do it across different demographic groups. For example, this is famous example, gender studies by an MIT student, Joy Bululani. And what she shows is that like these commercial face detection algorithms, Microsoft, IBM, and then Face++, they're really good at detecting white male faces. They're really pretty good at detecting white female faces, detecting black male faces. But the intersection of race and gender, they're really bad at detecting black women faces. And so this is showing, okay, across these different demographic groups, the accuracy is significantly lower for black women. And Joy also has like a very cool video on YouTube that's like a spoken word poem about talking about, okay, how commercial computer vision systems constantly misgender famous black women such as Michelle Obama or Oprah. And these types of metrics, or these types of classification parity metrics, are what's commonly used to enforce those legal regulations. So it's like the Equal Employment Opportunity Act, or things of that nature, are sort of using these types of classification metrics behind the scenes. So what's the most common one? So the most common one of these types of metrics is demographic parity. So demographic parity is like, how often do we get positive outcomes by different demographic groups or different protected groups? And this is what's really used to audit models for disparate impact. So like, who gets a loan or not? You look at different demographic groups and say that, okay, the positive rate, like, okay, the percentage of loans given to white men versus the percentage of loans given to non-whites, non-males, should be at most 20% difference. That's what that 80% rule means. They have to be within 80% of each other. And the thing about this is, like, that sounds nice. Okay, if we're a bank, you have to sort of balance out the number of loans you give to different populations. The thing is you can satisfy that immediate thing, but you could not really think about like the long-term consequences of your actions. And so this is a paper by researchers out of UC Berkeley, Delayed Impact of Fair Machine Learning, where they show that, okay, if you do this demographic balance for demographic parity, so you give the same percentage of loans to people in the orange population and people in the blue population, you're giving a lot more loans to people in the blue population who would then default on that loan. And as a result, their credit score goes down, and the overall credit score distribution for the blue population goes down as well. So if you just think about satisfying that immediate constraint of like, we just have to make the outcomes equal, positive outcomes equal, then you could harm them in the long run. And so another way to also think about this is that like when it comes to tech hiring of like, okay, we just need to hire, make sure the percentage of women we hire is equal to the number of percentage of men we hire for technical positions. Well, if those women leave in like 5-6 months because of a toxic workplace environment, do you really deserve your gold star for meeting that hiring quota? I don't think so. Next is parity of false positive rates. So this is really like as the name suggests, we're looking instead of like the positive outcomes, we're looking at the false positives. So really false positives, like the model says yes, but the actuality is no. And so this is sometimes called equal opportunity. And think about, like, if you think about what like false positive rate is, it's false positive over false positive plus true negative. So if you want to drop that false positive rate now, ideally you're focusing on dropping the number of false positives. But if you think about it, I could just drop the false positive rate down by increasing the number of true negatives in the system. And so let's say you're a police chief, and someone comes to you and says that, oh, hey, you're overly detaining too many black men, that the number of black men who you've arrested and not denying bail to or denying parole to, who would otherwise not go on to reoffend, is too high. So what can you do about this? How can you drop that false positive rate down? Well, ideally, you're sort of dropping the false positive. You're sort of granting more bail to black men who would otherwise not go on to reoffend. But you could also just increase the number of true negatives. So what's the true negative? So a true negative is a person who is arrested, they are released, and they don't go on to commit a crime. So who are those? Those are people who commit misdemeanors. So how can you increase the number of true negatives in the system? You arrest more people for misdemeanors and then let them go. Boom! That false positive rate goes down. Ta-da, you've achieved equality. Isn't that great? You just have to arrest more black men for misdemeanors. No, that's terrible. And if you don't think about it, you just optimize that metric and not think about like the societal factors that generate these numbers, you end up harming that vulnerable population we want to help. And finally, last one is calibration. So calibration is like a really hard thing to explain in layman's terms. Like it comes to statistical calibration. And really the way you think about this is like, for any event, like who wins a state in a political election, there's some true outcome. Like we know someone who wins, someone doesn't lose, and we're trying to figure out like how well are we actually predicting that outcome with our model. And so the way this is used in, let's say, recidivism, for example, where people are given scores, COMPAS scores from 1 to 10, or child protective services, where you give child is given a score of 1 to 20, representing how much danger this child is in. So like 1 being the child's not really in danger in this household, or 20 being like that child is in serious danger, get him out of the household now. And so how this works is, okay, CPS goes in, they evaluate the household, and they give the child a score between 1 to 20. And if that score is high enough, then above some threshold t, or which is say 15 for example, then you take the child out of the household because the child is in danger if they stay there. And the thing about statistical calibration is that like, really, if 2 people get the same score, that should be all that matters. If you have a white child who gets a score of 15 and a black child who gets a score of 15, they should be considered to be in the same danger level. They should both have like a 70% chance of being harmed or 75% chance of being harmed if they stay in that household. Like it shouldn't matter on like racial demographics, for example. It should just matter on like, okay, we evaluate the score, and that score is like the final thing. Like we take that score and we make decisions solely based on that score. And if this model is well calibrated, if like, okay, 15 is the cutoff for both, and we sort of get the same percentage of children being removed from households, from white households versus black households. And I guess the key idea is that like, okay, the scores should mean the same thing for same people. And so I guess like, before from my previous slides, when I talk about these metrics, there's usually like a little bullet point at the bottom that says danger, here's why this is bad. But I don't have this here. And why? Because I have a whole dedicated slide dedicated to what's the problem with calibration. And so anytime you give a talk on algorithmic fairness, you have to bring up this COMPAS example. So here's the obligatory COMPAS example. And I think this is an important case study. Because, so what was the issue with COMPAS? So this is that prison recidivism algorithm. So in 2016, the publication ProPublica says that, oh, hey, when you use COMPAS in order to decide who gets bail or not, you're detaining black defendants at a higher rate. You're detaining black defendants who, if they were released, they would go on to not reoffend again. And so ProPublica, Northpointe, which is the group that makes this COMPAS algorithm, their argument was that, no, our risk scores are well calibrated. If you get a score of 8 or above, we detain you. So the score models are well calibrated, but the issue is that the underlying distribution of the scores are not. So if we give scores of 8 or above a lot to black men, and we rarely give it to white males, for example, then okay, the chance of detaining a white male, because scores of 8 or above are rare for them, is low, but the chance of detaining a black male who has a score of 8 or above is high, because that they're more likely to have those higher scores, then, well, your model is not kind of racist. And the thing about this is, I think it also shows another aspect of using these metrics is that you can do really well according to one of these metrics, like statistical calibration, but do horribly compared to another metric, such as false positive rates. And so just trying to aimlessly optimize for these metrics will result in solutions that really don't actually translate well to the real world. So what can we do? And so I'm going to propose sort of a low quantitative, low-tech solution, which is really, let's write better documentation. And that might seem silly, but I think part of the issues we have now with AI ethics is that Silicon Valley is sort of insular. Silicon Valley believes it's filled with tech geniuses who have believe they have achieved the 13th level of cognition by drinking their salt juice and going in their cryo baths. And they don't need plebeian mortals to tell them how to do their job. They will take care of them by themselves. They don't need government regulations. They don't need outsiders to do their job. And that's not true at all. I think better documentation allows for better communication of how these data sets are built, how these models work. And so even if you're not trained as a cultural anthropologist or an ethicist, if you can better communicate the outcomes of your work, better communicate how this is trained, how this is tested, to those people, they can do the evaluation of okay, will this harm people in the long run? Will this accidentally harm these groups of people that you're not thinking about? And so here's this really cool idea of data seats for data sets. This is done by Timnit Gebru, Timnit for the stenographer. And she basically proposes well, other industries like the automobile industry or clinical testing, they sort of have standardizations of how they evaluate their models. And we should adopt something similar for data science data sets. And so if you think to automobile testing, for example, okay, historically, those automobile tests were tested on crash test dummies with prototypically adult male features. And as a result, in the real world, when actual automobile collisions happen, women and children were extremely harmed or more likely to be severely injured in those. And so now we have legal regulations saying okay, we need to make sure you also test on prototypically adult female dummies and child dummies. And this documentation, I think, will answer a lot of questions how was the data collected? Is this data collected in a way that doesn't exclude individuals? And I think this is very important because I do think a lot of the ways we think about machine learning is sort of focused on the models and not so much on the training set. We don't think about what makes a good training set a good training set? And you may think, okay, what makes a good training set? No missing data, no outliers. And that really answers the question of can I do statistical analysis on this or not? It doesn't answer did I exclude groups of individuals that I should care about? Did I exclude trans communities? Did I exclude non-heterosexual individuals from my data set just by the way I collected the data? I do think this shifts the conversation from the model to how do we actually collect good data that we've really not thought about before. Because we just sort of assume, okay, the data set it lives in the Aether. I got it from Kaggle or I got it from some other website. But we don't really think about is that data set actually suitable for my problem, or is it just conveniently available? And next, something similar for models. And so this is done out of Google research by Meg Mitchell's group, the Google AI Fairness group. And so what they propose is sort of something similar. So standardized documentation for machine learning models. You document, okay, how was this model, when you produce a model and train it before you deploy it, let's talk about how is it meant to be used? What are the intended use cases of this? How was it evaluated? And not just okay, is it looking at accuracy, calibration, or precision, but also how is it evaluated against different demographic groups? How is it evaluated against the intersection of those demographic groups? Because let's bring in intersectional analysis into how we do data science and machine learning. And I think also the key thing is what are those ethical concerns? So if you do design a sexuality classifier, what is the ethical concerns with that? How could this be used to harm people or be weaponized against people in countries where homosexuality is illegal? And the key thing about this is more transparent model reporting will allow us to better communicate how people should use our models. Because right now we sort of just okay, I want to do computer vision. Let's grab YOLONet or AlexNet and just apply it to all our problems, even though those models are not really designed for your specific problem. And finally, there's also this tool, Deon, which is an ethical checklist for data science projects. So this is Deon. It's produced by an organization called Driven Data. They do consulting with nonprofits, government organizations, and they also run data science for good competitions. So think Kaggle competitions, but with the definite emphasis on helping some social good aspect of helping teachers, helping education, helping drug treatment, for example. And what this tool does, it creates a markdown file in your repo with a checklist that checks for different things. So like, how was the data collected? Was it collected in a fair way? Did it actually cover all the groups of people you need to cover? Did you exclude a group of people? And also, were people informed of how their data set was collected? Like, informed consent is important in the social sciences. Like, you can't get research approval unless you have informed consent for your participants. But on the other hand, in data science, we're just able to run A/B tests on our users without telling them what we're doing so. And you can run some pretty horrible A/B tests on people that like, why the hell did you do this without having to inform them? And then also think about data storage. And I think this is important because we now sort of have this idea of like right to be forgotten, so that if someone doesn't want their data set to be data to be used in an algorithm, they should be able to say, I don't want my data to be used here, delete it from your records, and you should be able to do that easily. You should be able to comply with that as part of GDPR. And then also when you deploy the model, how do you think about taking it down? If it does come out that, okay, there's a news story that says like, oh, your model is harming these groups of people, how do you take your model out of production? And I think it's important to think about those beforehand. And I do want to know that like these things, like the model cards, the data sheets, and this checklist, they're not foolproof. Like, it's not a foolproof way to prevent you from harming groups of people that you don't want to harm. But I do think it's like a sort of good first step. It sort of helps us be a little less stupid when we do data science. And finally, I want to give a special shout out to the AI Now Institute. So this is a NYU research institute that looks at sort of like the cultural and societal impact of AI. And so they held this annual symposium on ethics, organizing, and accountability. And they also recently produced this paper talking about the diversity crisis in AI. So a lot of the things, all the issues with AI now, sort of like, we don't really have diversity. We don't have different voices or different opinions in the room. And this makes a lot of ad hoc solutions to like algorithmic fairness like kind of moot. Okay, if you talk about, okay, instead of just having an automated algorithm, and you just have a human in the loop to check decision. Well, if most of your humans in the loops are like straight white men, they don't really understand the lived experience of non-straight white men, and they won't be able to check for decisions that your algorithm makes that they don't realize that this is an issue for other people who are different from them. And so I think it's important because it also talks about like some of the more technical, long-term technical consequences of not having diversity in AI and machine learning and data science. And so that's really the end of the talk. Here are all the papers I referenced throughout the talk if you want to check them out afterwards. And yeah, I hope this talk was engaging. I hope you all learned something. And if you had the time, I hope you check out the other talk on measuring model fairness.